I'm Rob Futrick, PM lead for Azure's HPC software and services team. I'm here today to talk to you about Azure's HPC and AI capabilities. I'm joined by Wolfgang Gensch from UberCloud, who will be talking about their amazing HPC platform built on top of SUSE Rancher, as well as Daniel Gruber and Yagub Dabiri, who will be talking about the Living Heart project. So when we talk about Azure's HPC and AI capabilities, we talk about ourselves as a cloud built for HPC. What we mean by that is we're not a public cloud that has some HPC capabilities added on. Rather, we are a world-class supercomputing center that provides the same ease of use and flexibility and on-demand access that public cloud users expect. We marry the best-in-class HPC and AI hardware comparable to anything that you can buy on-prem with the scale and worldwide presence and flexible access and management capabilities that people expect from the public cloud. And what this means is that we enable our users and our partners to solve any HPC and AI workload at any scale. Now, we, as a public cloud, we offer general purpose hardware. We have our A series, D, F, you name it, that people use for their, their standard business applications, their websites, and data processing needs. And they expect to be able to go and with a click of a button, deploy that and manage it and use it over time. And to that system, we also offer our specialized VMs. And that could be our H series, which could be memory bandwidth optimized or dense compute targeted, or it could be our N series of accelerators, the NC and ND being GPU compute, the NV being visualization and remote desktop targeted, or even the NP, which is programmable FPGA fabrics. And I mentioned any scale, and that includes truly any scale, even up to Cray in Azure. And that could be the Cray XC or CS supercomputers, or even the Cray cluster store file systems that really enable you to go all the way from small scale to extreme scale MPI and file system needs. Because we are a best-in-class supercomputing center, we offer all this on top of our InfiniBand core. And that is what allows our users to achieve such small latencies and such incredible throughput, and to really drive those tightly coupled applications up to tens of thousands of cores per simulation, or an order of magnitude more for the clusters in general. Now, in those clusters and our HPC hardware, we offer the best price performance, and one of the ways we do that is by targeting our offerings towards the constrained resource in our users' workloads. The HB series is really aimed at memory bandwidth optimized compute. It's based on AMD processors. And the HC series is based on Intel Skylake processors in this case, and is aimed at dense compute. And our newest offering, the HBV3, is our flagship offering, is based on the AMD Milan processors, a cloud first. And it frankly offers the highest performance and the most cost-effective performance of any CPU for HPC. It is absolutely a performance leader in both the per VM, per core, and per cluster categories. Now, if you take that same kind of workload optimized approach to our GPU fleet, you really kind of see three categories emerge. You have light compute VMs, and these are all about low cost, especially low cost of persistent infrastructure and wide reach. We want to give you the AI capabilities when you need them, where you need them, at a cost that makes business sense for you. And this could be something like our T4 based VM offerings. Then we have the mid-range VMs, and this is all about flexibility and performance. This is where the vast majority of business-critical data is processed, and includes things like batch inferencing, analytics, and in general, just demanding business workloads. And that could be 1, 2, or 4-way V100 offerings with or without the InfiniBand fabric in order to provide the performance at a cost that makes sense, while differentiating from the high ambition VMs. Now, these are truly for expansive training needs, and they come anywhere from 8 GPUs up to thousands of GPUs, again, connected via that supercomputing fabric. And this really is aimed at our most ambitious users and allows them to scale up and scale out as their needs demand. And if you look at our GPU fleet over time and the infrastructure we have, it's clear we've been at this for many years. And over those years, we have both expanded the breadth of our offerings as well as the kind of workloads that they are targeted at. And you can see that go from all the way back in 2016, and as that's grown over time to go from real-time inference all the way up to model parallel training on, again, those A100-based SKUs. And that is clearly a strategy, and that is a momentum that we want to continue into the future. And so back in 2019, we had a cloud first with 20,000 core MPI job. The following year, in 2020, we quadrupled that up to an 80,000 core MPI job that was significantly faster and more scalable than anything else in the cloud. Along the way, we were the first to deploy AMD EPYC Rome processors in our HBV2, as well as 200 gigabit per second HDR InfiniBand, also in the HBV2. Later in 2020, we were the first to deploy a 1 terabyte per second parallel file system in the cloud. And then we followed that up in 2021 with a 1.6 terabit per second InfiniBand fabric for that NVIDIA A100 ambitious VM. And this is, again, a strategy we plan to continue well into the future. And what that really means is that Azure HPC and AI delivers real performance at scale. This could be the Star CCM scaled to 57,000 cores, running a 1 billion cell Le Mans model. Or it could be running Wharf or NAMD at over 80,000 cores. Or even our dedicated supercomputer capabilities for OpenAI with over 285,000 CPU cores and 10,000 GPUs. We offer the best performance per VM, the best overall performance per dollar, and the best scaling for HPC and AI in the cloud. And combined with our general purpose capabilities and that public cloud flexibility, scalability, reach, and management ease, we really are one cloud for all your workloads. You can take your existing applications, you can Azure enable them and drive a hybrid workflow, burst your workloads into Azure as needed, and optimize your use of on-premises and off-premises resources. You can clone your workloads to cloud and get up and running with a conceptual lift and shift without having to rewrite your applications or re-architect your workloads. You could port your entire application to the cloud and run in cloud workflows, or you could modernize your applications, possibly leveraging Azure's transformative services, whether that's Azure Synapse, Azure Data Lake, Azure Machine Learning, Azure Quantum, and many others, and create new differentiated services on which you can run your business. Now, our HPC and AI users are already kind of running at the limits of their abilities. Almost by definition, if you're doing HPC, you're pushing yourself to the edge, because if you could be doing more, you already would be doing more. And so in coming to cloud and taking advantage of this dynamic infrastructure and this scale and this competitive technologies, we want to enable you to do that without introducing complexity. And so one of the ways we do that is through our workload orchestration services. In particular, today we'll talk about Azure Batch and Azure Cycle Cloud. And not only do they enable you to easily take advantage of the networking, the storage, and the compute that Azure offers, but they also act as a bridge to integrate your transformative services, whether, as I said, it's machine learning, Synapse, Quantum, or others. Azure Batch is cloud-native job scheduling. It's HPC as a service model, the resources are cloud-based, and simply put, it is the easiest and most scalable way of running batch workloads in Azure. You give us your tasks and your jobs, your choice of VMs, and we will auto-scale them up and down as needed, and provide you comprehensive monitoring so you have full understanding of what's going on at the VM level, the job level, the workflow level. And Azure Batch is also a developer platform. It is a way to SaaS enable or Azure enable your existing workloads. And it supports all the common frameworks and languages you'd expect. Complementary to this is Azure Cycle Cloud. Azure Cycle Cloud is an HPC management plane for running traditional HPC schedulers in Azure. Out of the box, it supports Slurm, Grid Engine, PBS, LSF, and others, and has capabilities that enable you to Azure enable your own schedulers. Through those schedulers, it supports a hybrid or cloud bursting model, as well as cloud native execution. We have users all over the world, that are bursting their production workloads, in Slurm clusters and others from their on-premises data centers into Azure, providing their users an almost seamless way of accessing greater HPC capabilities. So let's take a look at how easy that is to do. So you're looking at the SUSECON application. We have the GUI here showing a couple of clusters here, and let's just say I'm Rob, and I'm a scientist, and I want to run some fluid dynamics, or maybe I want to run crash test simulations or physics modeling or risk modeling or whatever. So we'll say Rob, SUSECON. I have to pick where in the world I want to run this. And so for today, we'll run this in West US 2. I do have to pick my infrastructure here. And so I know I'm going to be running HPC applications. So I'm going to pick the HPV2 VMs. I want to make sure I don't run over my budget and run too wide by accident. And so I'm going to let Azure auto-scale the cluster for me, but I'm also going to set a limit here. And I know that 1200 cores, which equates to 10 HPV2s, should be more than enough for what I need. If I was running a throughput workload, I could take advantage of Azure Spot VMs in order to save money. In this particular case, I'm not. So I'll set my network. If I wanted to, I could attach a file share. Let's say I wanted to use Azure NetApp files for greater scalability in my HPC cluster, or even go to BGFS or Lustre or something even more scalable. I could attach those here. In this case, I'm going to use SUSECON's built-in NFS sharing in their Slurm cluster. And I could also do things like change my Slurm version. I could enable Slurm's job accounting, so I had a better understanding of the costs of what I'm running and set policies. And I can fully configure every aspect of this cluster, whether it's the images that are used, the software that's installed, users, you name it. And I can do that through SUSECON's built-in bootstrapping capabilities or through using Cloud Init. In this case, we'll go with the defaults. So I save my cluster. Now nothing's running yet. This is just the example, or a template, sorry. And I will quick set a budget. And that way, if I go over my limit, then I'll be notified. And now I'm ready to start. So in just a few minutes, this will spin up the cluster, and I will have a fully functional Slurm cluster with appropriate limits, appropriate warnings, and with the software and users I need in order to run my workloads. In the interest of time, we'll jump over to an existing cluster, and we'll connect to that, and we'll run some jobs. So simply pick the scheduler node, click the connect button, and get my connection string. I come over here to my Cloud Shell. Now I've already set up my user with an SSH key, so I'm able to log right in. And if I check the job queue, you can see there's nothing running in Slurm yet. But if I come over here and pick a simple job, just running hostname, something to exercise the cluster, and I submit it, you can now see there's a job in the queue. And if I come over here to SUSECON, it's already detected that I submitted work, and it has started auto-scaling the rest of the cluster so that my jobs will run. And in just a few minutes, the jobs will run, they'll complete. And shortly after that, SUSECON will detect that I no longer need that infrastructure. It will auto-scale it down. And that is just how easy it is to create a new Slurm cluster, submit some jobs, and get up and running in Azure HPC. Now I'll turn it over to Wolfgang, who can talk about UberCloud's amazing HPC platform, and followed by a description of the Living Heart project and the amazing work that they've done there.
Hello and welcome everybody to the second part of this keynote presentation. My name is Wolfgang Gensch, and I'm focusing on the UberCloud engineering simulation platform and the Living Heart project. Later on will be covered by Yaqub Dabiri from 3DT Holdings. After my presentation, we will hear from Daniel Gruber, our Director of Architecture, about the infrastructure that he has developed, especially for the Living Heart project. The logos you see here are from all the partners who have contributed to this amazing project. So let me quickly go first through UberCloud. Just briefly summarizing what is UberCloud for those who haven't heard about us so far. So UberCloud is a cloud services provider. So not just a cloud provider. We don't have compute resources. This is what Azure provides, but we are coming on top with a layer of services, which makes it easy to use these resources. We provide a secure, on-demand, browser-based self-service cloud platform. And on top of these cloud platforms, then there are application containers for high-performance computing, which are running on any Linux in any cloud, be it public, private, hybrid, and most recently even multi-cloud. And this infrastructure and the HPC containers are used by some of the largest companies in the world these days. And last but not least, proudly, UberCloud is a Microsoft Azure HPC partner since now 6 years. Okay, so I mentioned already the UberCloud engineering simulation platform, which here in this application is running on Azure. It consists clearly of the Microsoft Azure infrastructure. And on top, we have developed a management and services layer. And then on top, we have developed our high-performance computing containers for individual solvers like Ansys, Siemens, Simulia, etc., but also for very complex engineering workflows, which I will mention in a bit. Now to the second part of the technology, which are our HPC, or in this case here, CAE software containers. So these software containers, so let me move the picture a little bit up, yes. These CAE software containers, they have been enhanced especially for engineering workloads. So it's not just plain Docker for microservices, but we have further developed the 30 plus additional layers for high performance computing, which we call also in this context macro services. These applications are pre-installed, configured and tested before we hand them over to engineers. They're fully managed services on cloud and on-premise. And they can run on any Linux, virtual machines, bare metal, OpenStack, vSphere, Kubernetes, and so on and so on. And on the user side, they are coupled with Linux and Windows clients, such that the user is all familiar with and doesn't have anything to learn. So in summary, it's already my last slide. The Azure SUSE UberCloud platform provides the following strong technologies and benefits, etc. So first, like 8 years ago, we started developing HPC containers. Still today, they are unique, they are universal, they follow standards, OCI, for example. They are integrated with OpenStack, VMware, Kubernetes, SUSE Ranger recently, and many more. And they can run in public, private, hybrid, and as I already mentioned, proudly, multi-cloud environment based on SUSE Ranger with one set of tools, providing the same look and feel experience everywhere. So as I said, nothing new to learn, etc. And the big benefit is that they are running in customers' own cloud account, where very often, the large enterprises with their enterprise agreements, they get strong discounts from the cloud provider, which now the user can benefit from, which is not usually the case with other cloud service provider infrastructures. And they run on here dedicated, secure HPC servers. There are no multi-tenancy here. Every user owns, for the time of renting, her own software and hardware stack. The engineer, therefore, has sole control. It's really like a rental car model, and she owns the hardware software stack, and there is no third-party interference, control, etc., as you often will find in ISV clouds and in other cloud service providers' platforms. So the customization is a very strong benefit of this one. It's very flexible because of Kubernetes, because of the containers, and they can handle complex engineering workflows, such as custom workflows, which the users have developed over the many years, multiphysics, digital twins, big data analytics, AI, machine learning, anything basically which is data and compute intensive. And with that one, I'm for now done, and I will hand over to our next speaker, Daniel Gruber, our Director of Engineering. Thank you so far, and enjoy further. Bye-bye.
UberCloud's next generation HPC application platform allows enterprises to run any kind of HPC application on any cloud in the very same way. For that, UberCloud provides customized self-service portals for HPC engineers to start fully configured desktop-based HPC applications in the cloud. Using UberCloud's UC command line tool or container, management of HPC Kubernetes clusters can be easily integrated in any existing environment, such as HPC clusters regardless where they run, CI/CD and DevOps pipelines, workflow engines, or job submission portals. The fully configured HPC Kubernetes clusters require zero maintenance, as they are disposable and an update is just a simple destroy and recreate operation. Hundreds of clusters can be created and distributed across different cloud providers to exploit HPC capabilities like InfiniBand on Azure. For day-2 operations, our clusters seamlessly integrate with SUSE's Ranger platform. That gives operators all required tooling for visibility and diagnostics, monitoring and alerting, and centralized audit. A typical workflow of an HPC engineer working with UberCloud's platform looks as follows. First, the engineer selects the application, such as Abacus, ANSYS, or StarCCM in the self-service platform. Then the engineer gets a predefined choice of infrastructure hardware to select from. Afterwards, the infrastructure is deployed and the engineer gets a welcome email with the login details. Often DCV is used in order to access the remote desktop, as it provides a very smooth experience. Then the user can work with the application like on its own workstation, but with a much more powerful hardware in the background. When the engineer wants to run simulations which require to involve more compute nodes, he or she can just change the cluster size at any time to the desired size through a very simple to use self-service user interface. Once the engineer is finished with its work, he or she can shut down the cluster to keep cloud costs at a minimum. For the Living Hard project, we started a single node desktop with Abacus application and Abacus viewer installed. Batch processing was integrated in an external HPC workload manager. Each job scheduled by the workload manager is creating a cloud-based Kubernetes cluster, running one Abacus simulation, and deleting the cluster. This is as easy as executing 3 UberCloud commands. UC-create, which creates a fully configured HPC cluster based on AKS, GKE, or RKE. UC-run, which executes a batch job inside the containerized HPC application. And finally, UC-delete, which removes all allocated cloud resources. In total, we created more than 700 Kubernetes clusters, having running up to 30 of them simultaneously. Our main restriction for that was the availability of Abacus licenses. All clusters self-registered at Ranger, which was required to supervise the created cloud resources efficiently. Most interestingly for us was tracking the CPU usage, ensuring that all cores are used 100% during the simulation run. Thank you.
My name is Jakub Daviri. I am a scientist at 3TT Holdings, and I give you a short presentation about our work on modeling of the mitral valve. The mitral valve is placed between left atrium and left ventricle. This valve actually prevents blood leakage from the left ventricle to the left atrium. There could be problems with this valve, which leads to excessive leakage or regurgitation from the left ventricle to the left atrium, and actually excessive blood regurgitation can have life-threatening consequences. There is a therapy called mitral clip. It is a relatively new therapy for treatment of mitral regurgitation, and in this therapy, one or more clips are placed along the leaflet edge to reduce the mitral regurgitation. Actually, mitral clip intervention is currently based on the cardiologist experience. There isn't a systematic way to find the optimal number of clips or to find out the best location that the clip can be placed. So if the mitral clip is not placed in an optimal way, this intervention cannot be as effective. So it is important to inform the cardiologist about the optimal scenario for the intervention. We use computational modeling for this purpose, and here you see the result from one of our publication that shows the leaflet stress for two different locations of the mitral clip. So we use computational modeling, particularly we use a finite element method to create in silico models that simulate the outcomes of mitral clip therapy. In our method, we simulate both the structure, mechanics of the leaflet, as well as the flow of the blood, and we use a method called spherical particle hydrodynamics. For different number of clips and different locations of the clips, we do the simulations. We use Abacus fundamental package for this purpose, and the computations are done with the help of overcloud. Here you see an example. You see 3 different locations of the mitral clip, and you see the leaflet stress for each location. Based on these results, we are able to actually simulate what happens for different scenarios for the mitral clip intervention. The problem with computational modeling is that it is time consuming in our case. For example, for one model, we need several hours to do the computations, and it is not good for clinical application. In clinical application, we need real-time data. To resolve this problem, we use machine learning. So from these computations, we create a data set that has different locations, different numbers of clips, and we use this data set to make predictions using different machine learning algorithms. For example, decision trees, XGBoost, or deep learning methods. And actually, we have done this for other cardiac mechanics problems, and we have published results in papers. This work is supported by SPO NIH grant. Thank you.
Thank you for your time today. Really appreciate you listening to us talk about Azure HPC and AI capabilities, Uber Cloud's HPC platform, and the Living Heart project. If you'd like to learn more, you can go to Azure's website and learn both about our technologies and our offerings, as well as solutions for your industry. And you can also find ways of engaging partners as well as Microsoft in order to help implement your high-performance computing solutions. Thank you very much.